These are the pictures of the planets that most of the planets that people have seen with direct imaging, where you can actually look at the planet and hope to have a chance of getting a spectrum of it. These are not Earth-like planets. They're not even close to that. This is the original one Fomalhaut B that was detected, and you can barely see it in the dust ring here of this very young. These are all A stars, very young stars. This is junk around the star that's been covered up. In both of these cases, the star, in all three of these cases, the star at the center has been suppressed by a coronagraph of some type. You know, by putting your finger in front of the beam and blocking it at the photographic plate, or the CCD, or some other more fancy technique that we have lots of. So here's the junk that's left over from blocking the star, but you have planets labeled B. There's the, I'm killing it there, but it's inside that circle, B and C and D. These guys are going around in this sense here. We know that because we've seen this planet D move a little bit recently. And these are all pretty far away from the star. They're out at the distance of the outer planets in our solar system, and so is the one in Fomalhaut. This is 8799. And here we have Beta Pic. There's a planet. This is a composite picture of the dust disk seen edge on Beta Pic. This is the planet a couple of years ago. Here's the planet again last year. And so it has actually moved from this place to this place, and it's not a background star, so it really is a planet. So these are the good examples. If we were going to look at a solar system around each of these, the Earth orbit would fit in a very small circle on the inside of any one of these pictures here. These are all very large-scale pictures. So we need much better telescopes and much better coronagraph systems eventually for these things. Just some idea as to where we should be looking. Excuse me. This compares the kinds of things that we have up or in mind and where the stars are. And this is important for the reason that I'll just get to immediately. If this is the Earth and we want to look at the nearest 100 or so stars here, the reason we want to do that is because TPF, the Terrestrial Planet Finder, either coronagraph or O for occulter or I for interferometer, any one of these are all called, roughly speaking, terrestrial planet finder systems, are direct imaging systems, and they will give you the color and the spectrum of the planets and eventually signs of life. But in order to do this, you have to have this planetary system spread out enough on the sky so that you can see the planet separated from the star. And by separated, I mean like a tenth of an arc second away, which is awfully close. So you, tenth or a few tenths of an arc second away. So in order for them not to be even closer together, which is even harder to separate, closer together would be the stars that are very far away. You need the stars to be in the neighborhood of about 10 parsecs around the sun. If you go much beyond 10 parsecs around the sun, then things begin to get small and blurred. But if they're at that distance or closer, then we can separate them with coronagraphs or occulters or interferometers. So that's the reason I draw this little circle here. And once upon a time, well, until August 13th of this year, when the decadal survey came out and they said, we don't want to do SIM, this slide was a good slide. It's not a good slide anymore. It may be in another 20 years. But it could do astrometry around these nearby stars and tell you which ones have planets and what the masses of those planets are. Without that, we aren't going to have that information now. What we can do is we can point a telescope with a coronagraph at these stars one by one and see what we see and try to figure out the hard way what the masses of these planets are in addition to their spectra. But let me just point out what's going on today. Today we have Kepler and COROT. COROT is the European transit mission. It also does seismology, astroseismology, which I won't talk about. And Kepler does an identical thing. It looks at stars that are far away. And I've drawn them out here schematically because they're all at about a kiloparsec. They're not at the 10 parsec level around us. So these stars are really far away. They're all 13th, 14th, 15th magnitude as opposed to naked eye stars. And they cover a teeny tiny part of the sky, as you can see here. And Kepler has been, COROT was earlier than Kepler by a couple of years. Kepler has been dramatically more successful in finding stars, as you heard. And we have something like 400 or 400 candidates. Now, I said eventually what they announced before they started the mission was that they expected to find something on the order of 400 Earth-like planets, assuming that there was one per star. And that's a big issue, is how many planets of a given type are there per star up there in the sky? 2 days ago, I added the comment at the bottom here, building first. That's a mission that was newly invented in the middle of August from the decadal survey, saying that this is what we will do in this coming decade, between now and 2020. And half of that mission was dedicated to exoplanets in the sense that it is a single, pretty small telescope, 1.5 meter telescope, that focuses onto a large focal plane. And with that large focal plane, you can do things like looking out away from the galactic center to look for gravitational, for weak lensing of around galaxies, and so you can do dark energy. So half of the mission is a dark energy mission. The other half is a planet finding mission, which by coincidence also involves gravitational lensing, but in this case, it's the gravitational lensing that you heard about before of a star near the galactic center shining at you and having a foreground star, which is only a few kiloparsecs away, pass in front and then lens the light, bend it towards you a little bit, have the planet enhance that a little bit, and detect your planet that way. So it's about a 50-50. I've got 1 or 2 more slides. Is that okay?
You don't want discussion, it is.
Okay. Let's see what's on the slides and we'll see what. Okay, so the prospects are, I think I covered this, the prospects are, we have Perron Kepler right now. JW is planned, it will do transits of very large planets. This W1 is coming up, and basically in this whole business we're waiting in order to do a really good job on exoplanets for something which has not yet been decided and which will have to be decided when we have a better budget in this country and a more adventurous decadal survey committee. Apologies to those who are on the committee. That's all I have to say.
Yeah,
So
some questions and comments for Wes, please. Yes.
Yeah, with the idea of direct imaging, red edge, et cetera, there's never a discussion of the adding into the exoplanet mission SETI research and detecting of evidence of radio signals coming from those potential planets. Can you give us any background on any debate that happens behind the scenes about that?
Well, you're absolutely right. There is no discussion of searching for radio signals from these planets. We're finding ourselves hard put to even see the planets and detect the light, the visible light from them. I guess our assumption has been, and there's been no discussion behind the scenes, okay? The assumption is that SETI person is out there and searching for these things, and it's going on. Oh, excuse me, and Paul Horowitz. So, you know, the assumption is that this is going on and that you'll do the best job you can, and we're trying to catch up. We're way behind.
There was a time.
funding than we do.
You mean you have less than a few $1 million per year?
Yes.
All right, okay.
There was a time in the 90s when SETI was coupled with the search for exosolar planets called the TOPS program, and SETI had been renamed HRMS, High Resolution Microwave Survey, to try to hide it from those in Congress who wanted to kill it. Unfortunately, they found it and they killed both programs, so there's been a little bit of anxiety about trying to get too close together. But in reality, of course, these two programs are very much closely aligned. We have the same goal. We're looking for life elsewhere. Chris.
So it's a little discouraging because I think that most people don't realize that the Kepler Earth-like planets are extremely difficult to follow up. I mean, that faintness with JWST is an enormous challenge. So, I mean, the demotion of SIM and TPF sort of puts off the game. The next stage of the game is biosignatures, and it seems like that's being put off a bit because we have to work in the nearby volume of space to do that well.
Yeah, it's more than somewhat discouraging. It's very discouraging. I mean, it's unpleasant. Yeah, and the fact about the Kepler planets, to go back to those that you mentioned, is that they're so far away that the ones on the right there, that we can't even follow up on them. I mean, they will remain planet candidates for long and maybe forever because the systems are just so far away that we just have to rely on the transit signal, and that's all you get.
Guy.
Can't isolate it by itself.
Guy, please.
This is more of an inside baseball kind of question, but I think it goes to the mechanisms of how we're going to be searching these things. You've been talking about the decadal survey, which I assume is the astronomical decadal survey,
yes,
as opposed to the planetary decadal survey.
As opposed to,
and
yes,
there's this big debate in our grander field as to where exoplanets belong. Is it a branch of astronomy? Is it a branch of planetary science? who's paying for it, what buckets of money are available to it. Where do you see the state of play at the moment?
Well, as a member of the Division of Planetary Sciences, since Carl Sagan was in charge of it a long time, I consider myself to be a planetary scientist and an exoplanet scientist, and these are, as far as I'm concerned, the same topic. However, if you live at NASA headquarters, the astrophysics division is split into 3 parts there, or 4 parts, and there's, well, planetary is not even astrophysics, it's planetary, and then in planetary there's Mars, so you got Mars, you got planets that are not Mars, and then in astrophysics, it's 1/3 of astrophysics is theoretically exoplanets at NASA headquarters. It's definitely not the case that we have 1/3 of the budget done.
Woody?
One quick point is that the U.S. is not the entire Earth, and there are other things going on, and I'm not really aware. It'd be nice if someone could tell us about the European situation. But I'd also like to make a bold prediction. I think that when Kepler actually returns, some Earths, as much as we can tell, Earth-sized, Earth orbit, sun-like star, and so forth, that's going to create an incredible excitement. And I think that you will see money starting to shift around and flow, independent of decadal surveys and so forth.
I would hope so. To answer that question first, if the money in the United States depends entirely upon the people that live in the U.S. Congress, and if they decide that that's something,
that's what I mean. This is going to capture.
If they decide that that's something that's worth funding, then that's fine.
We don't realize the difference between
do this.
We all know they're going to find it, but the reality of it is just going to capture the popular imagination. They're going to say, we want to know more about that.
This may happen soon. I can tell you now, I can't show you a slide because I don't have it figured out entirely. But I think if you look at the data that Kepler has sent back so far from the first 42 days that they did a year ago spring, if you look at that data, you can extract out what number of planets they should have seen that are giant planets, and it matches up pretty well with what you would predict. And then you can look and see the numbers of small planets that they predict, which from the giant planets just go up on a curve that's on any kind of graph paper that you want to use. The number of small planets goes up dramatically. And if you use that to predict how many planets there should be of terrestrial size in habitable zones around stars, it comes out to be a large number. Not 1% or 10%, but it's a large number. So that needs to be worked on, but I think it can happen.
Please, Joseph.
Just 2 comments. The Europeans do have this Darwin mission concept. I haven't been following it closely, but
all right. So, I didn't answer that part of the question. So in Europe, all right. So the situation in Europe is very much the same as here in the sense of not having very much money, and they're even more acutely aware of it than we are. And there is a strong sense on both sides of NASA and ESA that there should be cooperation because they don't have so much money. And we no longer fly the national flag on our telescopes so much. I mean, it's more of a cooperative thing. And so I am hoping and expect that the decadal survey here will be looked at in Europe, and that there will be some coming together of these houses. That certainly the kinds of science that are being talked about on both sides are the same. For dark energy, at least they both have a dark energy mission, and so they really should be trying to combine them. As far as planets are concerned, exoplanets are concerned, Europe had the Darwin mission, which was 4 free-floating infrared cold telescopes and combining a beam in one place, and that's exactly the same as TPFI here. In fact, it's exactly technically the same now because after years of work, they've combined their ideas. But that idea has been dismissed in Europe, and it's been dismissed essentially in the United States as being too complicated. People think that interferometers are complicated, especially if they're cold interferometers. You know, as an interferometer builder and user on the ground, I know that they're complicated, but they're not impossible. So it's a naive point of view. But it is certainly true that room temperature single dish telescopes are simpler than multiple dish cryogenic telescopes free floating in space. And so I'm putting my money on the C part here, or possibly the O part, which is the Coulter.
Yeah, both ESA and NASA have long realized that they're running out of money, so they've been planning bilateral missions for quite some time. And in fact, just last week, John Morse, who's the Astrophysics Division Director, was in Europe talking about the decadal survey with the Europeans. If you want to find out what they decided, attend the Astrophysics Subcommittee meeting in Washington, D.C. Thursday and Friday this week. And or you can at least attend it by WebEx, and you'll find out what's going on. So, another question, please.
Yeah, I have a question about exploring extrasolar planets generally versus trying to find, say, signs of life or concentrating on the next Earth. I'm reminded of the debate in the 60s and 70s over big missions to Mars and whether the first landing on Mars should be something that characterizes the Martian environment as much as possible versus let's fly some experiments that go for signs of life. And there was kind of a split in the discipline, and life experiments wound up being on the Viking landers. And I wonder if there's...
So the question is, are we making the same mistake?
Yeah, and I certainly don't know enough. Right, is there a debate like this within the emerging discipline? Because we have the opportunity to learn a whole lot about planets and their nature and about solar systems, and we have statistics, and we can constrain the solar system theorists.
People frequently criticize, well, me, because I'm used to this kind of stuff, for searching for an Earth. And why are you focusing on an Earth? If it's 0.8 Earth, you aren't going to see it, or if it's 1.3 Earth, you're going to miss it. And the fact is that that's not the way this works. And Earth is just the hardest possible thing that we can think of to look for. Mars is out of sight and impossible. It's too small. Earth is right at the edge of every instrument that we can think of in the laboratory to build and theoretically design. It's 10 to the minus 10 in brightness. The Earth next to the Sun is a brightness of approximately 1 times 10 to the minus 10 in the visible. That's a huge contrast range at a separation of 1/10 of an arc second. That's why I spend all my time inventing coronagraphs that will separate these things and be able to get the spectra. But once you get the spectrum of a planet, then you've gotten all the information that you can. But this is this normal astrophysics technique. You go out to stars 100 years ago, use photographic plates, and you get spectra. We've been doing this for a long time. And so once you get a spectrum, the only question that you have then is what the resolution of the spectrum should be. And we've written papers on this a long time ago saying that the spectral resolution that you need for an Earth-like planet is approximately 70, because that allows you to resolve the oxygen A band. Not resolve it in the sense of anything dramatic, but see that it's different than the continuum next to it, that it's a dip. And that is the highest resolution that you need. A resolution of 70 or even less is perfectly good for doing all sorts of other science. You can see the colors of the planets, the reflectivity, the amount of Rayleigh scattering. You learn everything that you can within the bounds of your spectrometer. So it's a very broad-based search. If we have Jupiters and Uranus there, we can look at them. You can see big absorption lines of methane and other colors in the spectrum. So it is the most broad-based way of looking at something that I can think of.
Okay, one last comment.
This is the space-based perspective, but I think it's worth pointing out, especially people who haven't kept up with it, that adaptive optics on the ground has narrowed the gaps, a lot of the gap, the advantage of space and resolution. So we can make images now with the LVT that are as good as the cameras on the Space Telescope. So from ground you have a huge light buckets. The LVT, or the 20-meter telescope that we're planning for Chile, is designed with some of its primary goals involve nulling interferometry or coronagraphs and the detection of reflected light with sufficient photon gathering that you can make spectra. So I think biosignatures from the ground will be an emerging field in about 5 to 10 years.
Spoken as a true University of Arizona person. I would love to answer that. Can I respond to that?
Sure, yeah. I know you're going to anyway.
Advertised for some time, starting with the 100-meter telescope in Europe. Remember when the EELT was a 100-meter telescope instead of a 42-meter telescope, that they were going to detect Earths and they were going to get the spectrum of Earths. And it is true that you can get spectra of an Earth even though you're sitting on the Earth and looking out through it, because we've done that. We've looked at the light reflected from the sun off the dark side of the moon back down to the ground, and I've extracted the spectrum of the Earth, even though you're looking through the absorption lines of the Earth. So it is possible to do it. That was one of the objections. the objection that I would make to doing Earth detections from the ground is that there are not enough photons. If you calculate how many photons you need in order to smooth out a wavefront, which is what you need to do, you need to have a wavefront very smooth so that when you focus it, it can be focused to a perfect airy disk, and then you can have a perfect coronagraph, kill off your airy disk and the star, and just look for the stuff next to it. In order to not have speckles, you know, the stuff that was on one of these, I went in the wrong direction. These are speckles. The star is a teeny thing there. This is all the junk that you see at a normal ground-based telescope. In order to have a deformable mirror operating fast enough and over a wavelength, spatial scale of 10 centimeters or so, to smooth out that wavefront, you have to have a star that's very bright. And if you calculate how bright the star needs to be in order to see a 10 to the minus 10 planet, the star has to be about 100 times brighter than any star in the sky. So it just is not possible. And you can't do it with lasers in the sky because they're way too faint also. They don't have enough photons. So the idea of looking with ground-based telescopes, I think, is going to be limited to giant planets because they're brighter. You're never going to see an Earth-like planet on the ground.
You got another comment from back there? Did you, ma'am?
Me? Oh, yeah, I wanted to ask, is there a possibility that a Jupiter size or even a hot Jupiter might have a habitable planet? I mean, there'd be no way we could ever figure out anything about it with present-day technology, but is that a possibility even?
Sure. Well,
habitable,
sure, in the sense that
moon, I mean.
you can have a planet that's much closer, like these hot Earths or hot super Earths or things that are close, or a satellite around the Jupiter that are close to their star, if you're talking about the hot planets. Because on these hot planets, if the planet becomes too close to the star, it becomes tidally locked, then you have just one side facing the star, it gets baked and it gets molten, and the other side is freezing. But there is this zone in between where usually there's circulation on the planet, and so it isn't a hot and cold situation entirely. The atmosphere circulates around and sort of evens things out. But at this band, the sunrise and sunset band, permanently around the edge of the planet, is a perfectly possible place for life to form.
And we're talking about, do hot Jupiters have moons? Can they have moons, or is it a tidal problem?
I don't see any reason why not. Maybe a dynamicist would see a reason why you couldn't have a moon that close to a star. But
They're destroyed by the aircosmic effect, so they're unstable.
Okay, you just got your answer. They won't have moons.
Thank you.
But you can perfectly well have moons farther away. I mean, you know, life on a planet, on the moon around Jupiter, as everybody says, is conceivable, but we don't know how to find it.
So Jay gave us a special dispensation on extra time for the session, but in the interest of trying to finish up in the last few minutes, I will forget about my comments, and let's change gears and go to Lucas, who's going to give us a little bit about philosophy.
All right.